Welcome again to the Kiel Imaging Seminar. It is great to have you all here today. We have a fantastic speaker today. So it is my pleasure to introduce Dr. Schulte, who is a senior scientist in the Applied Science Laboratory of GE Healthcare in Munich. And he has studied electrical engineering at the University of Karlsruhe in Germany, did his PhD in magnetic resonance spectroscopy at the Swiss Federal Institute of Technology, ETH, in Zurich. And in 2005, Dr. Schulte joined the GE Global Research, as a scientist working on technology development around MR spectroscopy, RF pulse design, and imaging reconstruction and parallel transmit. He built the 13C MMR project in Munich, including a research team around it with multiple PhD students in close collaboration with the Technical University of Munich. And the MR software, which came out of this project, is of course used globally at multiple academic partners. And he moved to GE Healthcare in 2017 and is in charge of X-nuclei MRI at GE at the moment. Before we start, to the audience, please wait with your questions until the end of the presentation, until the discussion. And with this, Rolf Schulte, the stage is yours.
Thank you very much, Josh, for the kind introduction. So I will talk about acquisition methods for X-nuclear MR. First of all, why are we all doing that? And that is a great sketch from one of my favorite books from Guillaume, X-nuclear magnetic resonance imaging. And here you can see the high potential of X-nuclear MR. Basically, there's a lot of nuclei which are important in cell metabolism. And so for proton, we can do different imaging technologies. Deuterium, normally we can see we label the glucose and see the conversion into lactate, glutamate, glutamine. Lithium is taken up into the cells. For psychiatric disorders, carbon-13, often we use the pyruvate, and that gets taken up into the cell and converted into lactate, alanine, CO2, which is in equilibrium with bicarbonate. We have oxygen, which we can detect directly, although it's very expensive, but we directly get a measure of oxygen consumption with that in the cells. F19, there are certain substances, perfluorocarbons, which can taken up. You can use it for like stem cell tracking. Sodium is of great interest for the ion exchange. A lot of the energy in the body is used for the sodium pump, a huge amount of energy actually. Phosphorus, we can see directly the energy substrates, ATP and phosphocreatine and organic phosphates. Fluorine is another salt which is important in the equilibrium there, and potassium also. So what is X-nuclear MR? I mean, there are different names around and they can be confusing. But basically it's all the same. X-nuclear MR means everything but protons, multinuclear spectroscopy, MNS, or on other vendors it's also called the multinuclear option. It's all the same. Common nuclei are phosphorus, carbon-13, sodium, xenon, deuterium. There's a lot of more nuclei which have NMR active, which are NMR active, like 40 or more. Most of them are not so relevant for in vivo applications. I mean, those are the most relevant ones, and then there's maybe another 5 to 10 which people did experiments on. The main difference is different gyromagnetic ratio, and they all, apart from tritium, resonate at lower frequencies as compared to protons. You need additional hardware. The main constraint is always sensitivity. Even if you're hyperpolarized, the main constraint is still sensitivity, which has big implications on acquisition schemes later. And the main benefit of X-nuclear MR is that you get direct metabolic and functional information. The requisites for doing that is you need to have broadband MR hardware. You need to have dedicated RF coils resonating at those frequencies. If you want to do pre-polarized MR, you need a polarizer for C13 or xenon most commonly. If you want to do the other nuclei, you don't need it. You need sequences, you need reconstructions, post-processing. Often you need ethics approval. If you want to inject something, you definitely need ethics approval. You need good clinical questions. And then last but not least, you also need experience. It's usually not that straightforward as proton MRI. In terms of broadband MR hardware, you need a broadband amplifier. And on the GE scanners, it's a CPC 8 kilowatt amplifier resonating between 10 and 130 megahertz. And that's shown on the right-hand side. It's quite a large amplifier and relatively pricey. So the upgrade is also, because of the hardware, relatively pricey. You need a MNS exciter board. You need the MNS receiver. Usually people want multi-channel receivers. 3T is most common. And in my opinion, if you want to have clinical relevance, you need to get it running on 3T. However, 7T has a lot of advantages because of higher thermal signal. I mean, you gain a lot of SNR without the disadvantage of proton MRI, where you already have dielectric effects. So you can boost your SNR quite a bit, and often you have better chemical separation and so on. But as I said, I mean, 3T scanners are far more abundant worldwide. So if you want to answer clinical questions, you have to get it running on 3T. Lower fields are usually not very common, 1.5T. If you use pre-polarization, xenon or 13C, it doesn't really matter. For other nuclei, it's better to use higher field. And the challenge for us as vendors is that you have no RF contaminations in multiple frequency bands, and that is quite difficult nowadays because there's more and more electronics getting into the scan room. You have monitors, or this injector pump from Metrod, the new one, has a lot of noise on sodium frequency, for instance. So it's a lot of potential sources, and it's quite challenging to get those bands free. You need dedicated RF coils. There are many different nuclei and applications existing, and basically, you really need to make sure you need to know what kind of studies you want to do, which kind of organ, and then buy the dedicated coil for that. They're usually custom built by third-party coil vendors. The large vendors normally don't produce them. I mean, it's the strength of large vendors is more large quantities, and those are very specialized. So normally you go to those vendors. And then we are in a low frequency range. That's a mixed noise regime. That means good coils matter far, far more for X-nuclear MR as compared to proton. So even with proton, even lousy coils and proton MRI can give really good images. For MNS, it's very different. And there's also noise penalty if you have too many receive channels. And for brain, often a good start is a birdcage coil, especially at lower frequencies. Then you also don't need coil combination. Normally, you also want to have good proton images. So that means we need dual tune coils. That means often there are two resonance circuits in one mechanical structure, but electrically separate. Normally, you can also have it in one electrical structure, but normally it's different coils in one housing. And then that you can do the proton MRI. And then you also need to make sure that it's safe to operate. So you have to put proton blocking on the X-nuclear circuits and vice versa in order to be able to use them inside transmit coils. And then if the goal is studies, my recommendation is usually keep it simple. I mean, if you have technical developments as a main goal, you might go very complicated. However, like we are SNR limited, so normally you don't really gain from parallel imaging. You just need a long scan time, and then parallel imaging often doesn't gain you that much. So if you want to have higher SNR at the edge, then multi-channel coils are really good. Often inside the coil, they are similar SNR as bird cage coils. For sequences, the objective is to fill K-space in a suitable way. Shown here is 2 spatial dimensions. If you have 3D, it's just one more, but it's easier to illustrate here. So on the left is imaging. There you just have to fill the K-space in whatever manner you like. If you want to do spectroscopic imaging shown on the right, then you have to fill both the 2D spatial dimensions, and the time is the spectral dimension. So you need to go through this 3D space as good as possible. I think I also have a laser pointer. So this space you have to fill well. There are different trajectories. We typically distinguish between Cartesian and non-Cartesian. Cartesian, that means it's sampling on a Cartesian grid. The advantage is that simple reconstruction is just a fast Fourier transformation, and the reconstruction separates, so you don't need to solve everything in a big step, but you can do it one after the other. Artifact behavior is often nicer. The disadvantage is often that it's less encoding efficient. Non-Cartesian is shown on the right. Basically, some examples are like spiral, radial, rosette or so. Radial is probably the most common non-Cartesian trajectory, and then spiral, but they are not very common in proton MRI because of artifacts. For lower frequencies, I think the advantages outweigh the disadvantages. The advantages are that it's more sampling efficient and that the sampling starts in the center of K-space. So if you have very short T2 spins, then you can optimally utilize the SNR by starting in the center. The disadvantages are that the reconstruction is more involved and the artifact behavior is often more difficult. For spirals, like it's blurring, which people don't like. The very basic spectroscopic imaging sequence is shown on the left. We have, in this case, a slice selective excitation. You can also do hard pulse without the Z and do phase encoding along Z. Then you have 3D. In this case, we have 2 spatial dimensions, and we encode it with phase encoding. And each excitation is 1 point in K-space. And by just going up in time, we sample the spectral dimension. And that's also known as chemical shift imaging, and that is identical. It's just a different name. I think the most common name nowadays is MR spectroscopic imaging. What nuclei can we investigate? There's a lot of different nuclei. Deuterium has a relatively short T1 of like 50 to 350 milliseconds. T2 is quite short. Frequency is 20 megahertz. Natural abundance is extremely low. And we can use it for metabolism, perfusion. Then we have lithium. Lithium has relatively long T1 times, depending on field strength. 7 Tesla has like 6-7 seconds. 3T has like 3 seconds. 1.5 T is shorter. T2 is relatively short, around 50 milliseconds, I think, for the normal lithium salt. And that is because it's a quadrupolar moment. It's resonating at 50 megahertz, very high natural abundance, but it's very rare in body, and usually it's used as a psychiatric drug, and then you can detect it. 17O is a different isotope from the normal oxygen we normally image. We normally have an H2O, and that is extremely expensive. It's mostly done preclinically. However, it's very nice for oxygen metabolism. T1, T2 times are really short, and frequency is 17 megahertz at 3T. 19F is quite a popular field, also mostly preclinically. It hasn't really translated into the clinics, mostly because of sensitivity limitations. T1s are really long, T2 relatively long. It's close to proton frequency, 120 megahertz, as compared to 127 megahertz at 3T. And we can use it for like cell tracking, or you can also inhale fluorinated gases to do lung imaging. Sodium is probably one of the most popular nuclei currently. T1 is short, T2 is extremely short. Frequency is 33 megahertz, and that is the ion imaging. So that's a marker for cell function. And phosphorus was one of the very first methods, even before protons, I think, around for 40 years. A lot of the nuclei are around for a very long time, and phosphorus has quite long T1 times. It has quite high resonance frequency, 52 megahertz, high natural abundance. And especially in muscle, we can see it really well. And brain and heart, it's more difficult, and that's used for like metabolism, pH, or tumor marker. Deuterium is very popular currently. It has a spin 1, and spin 1 means it has a quadrupolar moment. That means usually the T2 star, the T2s are very short. The natural abundance is very low. However, we can still see water in the brain with 0.015% natural abundance, but the voxels are like 2 centimeters in that dimension. Typically, people ingest deuterated label compounds. The most common one currently is glucose, labeled in the 6th position. You ingest it, you wait like 60 minutes, you can do your proton scans in the meantime, and then you have the glucose being taken up by the digestive system, and then you can do your imaging, like for instance, in the brain, abdomen, or whatsoever. It converts into lactate and glutamine, glutamate, which we cannot separate at 3T. So usually it's GLX only. T2 star is very short. That means we overlap quite heavily. Applications are metabolic disorders, tumors, neuro. There are some really good Alzheimer's studies now. In some countries, PET is a clinical tool for some of those neuro degenerative diseases, and possibly we can replace PET with deuterium, even though the resolutions are low, but probably they're good enough on 3D. Here are some results, some exemplary results from various sites. Mostly it's 3T sites. As mentioned, I think we need to get it running on 3T to have clinical relevance. On the bottom left is 70, PISA is 70, the rest is 3T sites. And they use it now for all sorts of different applications. You can gain SNR with SSFP, and on higher field strength, the properties are such that we can still resolve it spectric, that we can distinguish the different peaks spectroscopically. However, at 3T, that is not really possible anymore because of the BSSFP condition. If we want to gain SNR, the TR needs to be much shorter than T2. And then if the TR is much shorter than T2, then the acquisition time is too short, so we cannot resolve it anymore. Also, another encoding would be the frequency response of the BSSFP train, but that's also very ill-posed, so we can't really resolve it spectroscopically, but we can use it as a metabolite-weighted image contrast. And on the right, there's example. Sorry, that should be proton. We wish we could get that high resolutions with deuterium. So this is proton GRE. And this is the normal MRSI. In this case, a pseudo image is shown with proton MRI, with deuterium MRSI. We can separate glutamate. We can separate glucose, water, and GLX and lactate sometimes if there's sufficient amount. With SSFP, we can gain quite a bit of spatial resolution. So you can see much more of the structure of the brain and not only a blob. However, we can't separate it anymore. And if you go to like 20 by 20 by 20, then it's mostly noisy. Phosphorus is 52 megahertz at 3T, has a spin 1/2, so it has relatively long T2 times, is 100% natural abundance, and has endogenous signal. Applications are energy metabolism in the muscle. You can basically, with a surface coil, in one shot, you get a nice spectrum. And then you can do an exercise, which is shown here. If you exercise the correct muscle, you can see the phosphocreatine going down and the inorganic phosphate going up. And that is a direct marker of various muscle disorders. And then when you stop your exercise, you can see it's recovering relatively fast again. So this period was the exercise, and then it goes back up again. Sequences are unlocalized FID in the muscle or 2D, 3D MRSI. There's also a technique ISIS. It's not a terror organization, but it's basically a FID-based spatial voxel localization, but there's no advantage. I mean, you can just do a 3D MRSI. You need a long acquisition time anyway. So I think it's mostly legacy from people being in the field a very long time using that. Sodium. That's some sodium on here on this delicious bread from Titus. Basics, it's 100% natural abundance. It has very high endogenous signal. It's 34 megahertz at 3T. It's a spin 3/2, and that means it's a quadrupolar moment, has short T1 and T2 times. In tissue, the T1 is about 30 milliseconds, and T2, there are two different components in tissue. The predominant component is 16, it's relatively longer, it's 16 milliseconds. The short component is 2.5 milliseconds. So quantification gets very complicated because of different relaxation times. CSF, cerebrospinal fluid, and saline has much longer T1 and T2 times, but CSF is less biologically interesting. Usually people want to see the changes of sodium in the cells. They're really well buffered, so mostly what you see is the outer cell component. So it's still SNR limited, even though we get some images. That means we need long scan times. That means we don't really have to be very fast with our encoding. Applications as tissue viability, cell integrity, function, stroke, tumors, cartilage, muscle, kidneys. Also diagnosis, disease progression, and response to therapy. And sequences basically 3D gradient echo, and then you can use different variants. Usually it's good to have a center out trajectory. You need to optimize the parameters for the T1, given T1 and T2 terms. So normally the TR should be shorter than T1 and then use the Ernst angle. That is shown on the right, where I plot SNR per unit time at Ernst angle excitation. So if you have TR equals T1, you're close, you're more than 95%. So you don't gain that much. If you use like 5 times T1, you lose a lot of SNR. So basically it's very advantageous to have TR shorter T1 and use the Ernst angle. But then the SAR goes up, and then you might, if you SAR limited, then it's better to increase the TR a bit and still use the Ernst angle. Optimization with T2, we have T2 short and T2 long components. And then basically what we need is to sample the FID. If you have one component, it's easy. Normally, you sample it like 1.5 times T1 to be SNR optimal and apodize it with exactly the same filter. That's the matched filter, which Richard Ernst described in his book for NMR. It's the same here also. Basically, if we apodize the data with exactly the same T2 star we have, we get SNR optimal images. You lose, of course, resolution, but you can design it all to higher resolutions, and then you, in the end, gain SNR and resolution. Gaussian optimization is relatively close to this by exponential decay, and then for sodium, a good compromise is like 15 milliseconds. If you have it longer, you are restricting your TR. If you're shorter, you're not capturing the whole SNR. Yeah. There are different trajectories you can use. A while ago, I had an ISMM abstract on that, and basically, we want a center out trajectory, the optimum if you don't have any T2 star decay and apodization as Cartesian. However, for sodium, there's a heavy T2 star decay, so the optimum is different. It's not Cartesian anymore. It's very low SNR, so we want long acquisition duration, so we really should use 3D. And then there are different trajectories you can use: traditional, radial, density adapted, Cartesian, fluoride rotated spiral counts. I designed various trajectories and then compared them, and the result is that they're all relatively comparable. Cartesian has quite a bit lower SNR. However, that is mostly because the trajectory duration starts not in the center of K-space. If you were to use something like homodyne reconstruction, you could probably recover a little bit. If you look at the other acquisition methods, the SNR, there's some differences. You have to be extremely careful with correcting for the exact point spread function in 3D. If you have 10% error, it's already 30% difference in SNR, which sounds like a lot. If you correct for all that, the differences are rather small, and then in my opinion, it's best to use like an easy trajectory, which is less encoding efficient. However, it's very easy to implement a density adapted radial. If you want to be faster, then it makes sense to try the other trajectories, but then your resolutions will be lower. Yeah, main limitation of X-nuclear MR is SNR. Generally, we have very low sensitivity due to low concentrations, low gammas. Normally, we have huge voxels, region of interest. We acquire for a very long time because of averaging. If you have a very encoding efficient sequences, you would just have to average more, and then it doesn't really make any sense. And also it means fancy encoding techniques are highly limited. One way around that is hyperpolarization. You can align the spins outside the MR scanners. In MRI, we typically have every millionth spin aligned with a magnetic field, which is not a lot. If you do that outside, you can, with an external device, you can align like 50%. So you can boost your MR signal by 4 to 5 orders of magnitude. On the right, for instance, is a single shot acquisition of urea, and then below is 65 hours averaged, and you can see it a bit. The text is on top, but it's very low SNR. But it's also not a very fair comparison because you inject it and then it also gets diluted a lot. But you need an external device called a hyperpolarizer. There are different methods around. One is dynamic dissolution dynamic nuclear polarization, and that you can use for carbon-13, 15N. You can also use it for protons or xenon or other nuclei. Most common is really C13. For noble gases, we use a technology called SEOP, spin exchange optical pumping. On the right is such a polarizer. You have a laser, you have a cell where you have a rubidium atom. You shine with a laser on it, and then by collision, you can transfer the spins from the rubidium to the gas. And then at the end, you freeze out the gas in liquid nitrogen, and then that's a mixture in here. So you want the pure xenon, so you separate it by liquid nitrogen, and then you can walk slowly to your patient or volunteer. The T1 times are like 2 hours, 1 or 2 hours in the back, so you don't have to hurry so much. In C13, we have like a minute T1, so you have to be much faster. And the last method, which gained a lot of traction recently, is FIP, para-hydrogen-induced polarization. That's basically a chemical method. You replace the technical complexity, the cryogenics, and so on, you replace with chemical complexity. If you want to get high polarization levels, you also need you need to deuterate your catalyst, and that also gets extremely expensive and complicated. And also this technique is probably another 10 years until we can see it in humans. DNP and CEOP is currently used already in humans. The nuclei we can hyperpolarize. I mean, we can, in principle, polarize protons. However, T1 is relatively short. It's not that interesting clinically. And that you could use for perfusion. So if you have a catheter directly, maybe into your heart, you could see something, but it's quite invasive then. 3 helium was used quite a bit. It's hours in cell, minutes in vivo. It's 97 megahertz at 3T. However, 3 helium is very difficult to get nowadays. It's mostly used, I think, in missile heads for the, if I'm not wrong. It has some military applications, and basically the field died out because of cost and availability of 3 helium. Instead, the field moved to xenon. Xenon also has hours in cell, minutes in vivo, 35 megahertz. The images the ventilation images are not as good as for helium-3 maybe, but the big advantage is that xenon gets taken up into the bloodstream, and spectroscopically you can also detect the uptake, and then you get the lung function. So it's, in my opinion, more powerful than helium-3. Carbon-13, it depends which nucleus you have. You have T1 times of around a minute, 32 megahertz. It's 1% natural abundance. So basically you take enriched carbon compounds and polarize them. 15N, there's some really impressive 15N results around where you have T1 times of more than 5 minutes, and you can still see signal after like 5 minutes in vivo. However, it doesn't really metabolize, so it's mostly perfusion agent. Magnetization is very precious, so that means there's no recovery. Once you have T1 decay and once you excite it, it's gone. So you have to use your magnetization very smartly. That means you need efficient acquisition. So here, that's a big playground for all kinds of sampling strategies, different sequences, and so on. You need to use it efficiently, and also you must be fast in comparison to T1. If you have a sequence which takes 10 minutes, but after 20 seconds all is gone, it's a bit useless. And also it means the observable processes, the metabolism must be fast in comparison to T1, which in case of pyruvate it is. It also means it limits pre-scanning. For pyruvate, typically we use an external syringe. For xenon, you inhale a small dose before, mostly to get the center frequency. Yeah, C13 is 32 megahertz, spin 1/2, injection of hyperpolarized compounds, either in the tailvein and rats, mice, or in the arm. You see the metabolic conversion to lactate alanine bicarbonate. You can also do it thermally polarized. I mean, that was also a research field like 30 years ago, but it's not very interesting. I mean, basically, you average half an hour to get one single spectrum of the brain. Preclinically, you can do a bit more, but the processes are known, and it's not really that sensitive that you can use it for clinical applications. So applications of hyperpolarized C13 as altered metabolism, tumor, cardio, neuro. There's some really nice studies where they predict treatment response. If you can save a tumor treatment, which costs tens to hundreds of thousands of euros, then this relatively expensive method might make it. Then you can actually save money with it. Sequences, I mean, all sorts of accelerated MR spectroscopic imaging, or very common nowadays is also spectrospatial excitation with a single shot readout. Why do we use C13? Because it's a stable isotope, it's MR active, it has negligible in vivo signal, and carbon is important in metabolism. The definition of organic substances is that carbon is inside. So every carbon is everywhere. And why do we use mostly pyruvate labeled in the 1 position? The 1 position has a really long T1 time. It's not toxic it's endogenous, relatively non-toxic to relatively high doses. Metabolism is really fast, and you can separate it via the chemical shift. That is shown here. So pyruvate, you inject it, it gets transported in the bloodstream to the cell. Then you have MCT transporters bringing the pyruvate into the cell, and then it's enzymatically converted into lactate alanine bicarbonate. And you can see here that the peaks are relatively well resolved. So you can use all sorts of fast you can undersample the spectrum and use it to accelerate your acquisitions. Consensus more or less in the field is that spectrospatial is the way to go. And then there's a discussion what the best readout is. Some favor spiral, some EPI. So spectrospatial basically means you separate your spectral encoding. You don't do it in the readout, but you do it already in the excitation. You just excite a single resonance and a single slice. And that means if you have a single shot readout, that you can get one image with one excitation. And then we do that for we iterate through different metabolites. So we shift the spectrospatial pulse to the different metabolites. We have multiple slices, and then you can also do that with different flip angles. That means you can also preserve magnetization. Use the lower one on pyruvate, which is the precursor. You don't want to deplete the pyruvate, and use higher ones on the downstream metabolites. Because we had, I mean, people are disagreeing if spiral or EPI is better. And we had a course in Aarhus a year ago or 1.5 years ago. And we had some pick experiment. And then I used the chance to do a direct sequence comparison in a single excitation that we iterated between spiral and EPI readouts. The results basically is artifact behavior is a bit different. If you look at spirals, when the bolus arrives, you have those blurs. In EPI, you have like additional peaks. And then it's a matter of what you like more. If you like additional signal or if you like this blurring. Normally, people only look at later time steps where you don't really have it anymore. You can relatively easy get rid of that artifact by just skipping the first time steps. And I designed it to have the same real resolutions. However, EPI was still a bit higher resolution, while spiral had better SNR. Xenon is 35 megahertz, spin 1/2, 26% natural abundance. You inhale the hyperpolarized gas. The gas uptake is the direct measure of lung function. And then applications are like long COVID, asthma, COPD, cystic fibrosis, interstitial lung disease. And then sequences for lung ventilation, basically it's imaging. You do 2D, 3D, gradient echo or BSSFP. For functional imaging, you need spectroscopic imaging, and then you have 3 peaks, so you need at least 4 echo times to be robust. And yeah, finally, a word. I haven't talked so much about reconstruction. That is some work I did for call combination. We have very noisy data, and then people always want more and more receive channels. So we had some data from a 32 channel abdominal coil and basically saw mostly noise. And then I used a method which UCSF published, least squares fitting instead of SVD, and basically I could improve it a bit. And if you use noise decorrelation and least squares fitting, you can actually get quite a bit better results out. And then if you look at the spectrum, like, here you don't really see anything anymore in the noise, but with this method, you can recover a bit of the noise. If you don't use so many receive channels to start with, you don't really have that problem. If you look at phosphorus, xenon, or yeah, you gain not that much anymore. It's mostly at lower frequencies, and if you have an excessive amount of receive channels. The way you can do all those different acquisition schemes is with a MNS research pack, Fidel sequence. So the MNS product is relatively basic, and each nucleus application requires a different optimized sequence. And the idea was to provide complete flexibility for advanced users by reading an arbitrary RF waveforms, Bloch-Siegert off-resonance pulse, arbitrary gradients, and then you can read modulations for flip angles, TRs, TE, phases, and so on. And then there's a lot of changes for like hyperpolarized C13 experiments, xenon, and so on, and also proton spectroscopy now. And then there are different plugins, waveforms, and reconstructions. One is for pre-scan, ideal spiral CSI, and so on. The idea is to outsource EPIC, the GE pulse programming, to MATLAB. So what I can do in Fidel in a day or less takes me usually in EPIC a year or more. And then from MR30 on, it's part of product. However, not the waveforms and the reconstructions. I have different plugins coming along with it. Semi-automatic pre-scan is for all nuclei important. Then we have for deuterium, phosphorus, density-weighted 3D MRSI. Density weighting doesn't gain you that much, but we need to average a long time anyway, so it doesn't hurt. And then sodium, the available example in there is density-adapted center-out radial. For C13, a spectrospatial excitation with single-shot spiral readout or ideal spiral CSA. For xenon, is 2D GRE, 3D BSSFP, or 3D MRSI. It's around a bit more than 40 sites using that globally. Some use the compiled in examples. Some are quite actively putting stuff in themselves. You might ask, there's a lot of open sequence discussion. Currently, PulseSec is a very hot topic. How does it compare to PulseSec? So both are tools for rapid sequence prototyping. Fidel has many modulations. You read in a lot of stuff, but the core is still a base. The core base sequence is still static. So it's good for like FID, gradient echo, BSSFP, but if you want to do like spin echo sequences or virus preparation blocks, it quickly reaches its limits. It's optimized for X-nuclei MR, but people also use it for proton MRI and also spectroscopic imaging. And then it's part of product, but not the waveforms recon and so on. There you still need to go through the processes. The idea was that we can have that downloadable, but wasn't allowed. It runs smoothly on the last from HD16, so the last 15 years of generation of GE Healthcare MRI scanners. It runs on all of them and without much trouble. PulseSec, the interpreter PGE2 on healthcare. So the pulse comparison is specific to healthcare, to GE. It's completely flexible, and most things are possible. But you still need to debug for individual scanners and sequences. Often the timings are a bit different. We had a PhD student from Columbia trying 3D EPI, and she got already a prototype, but that was another scanner, so she still needed like 3 months to optimize it. X-nuclei still needs further debugging integration. I'm not so sure what real-time feedback there is if you can use gating and graphical prescription. I think graphical prescription now works, but Matteo Cencini and John Frederick Nielsen are actively working on it, so it will improve further. So those question marks will probably disappear. And then both basically are platforms, and the usefulness comes from the plugins. And then, I mean, if you want to have PulseSec to be useful for hyperpoised or X-nuclei experiments, basically somebody needs to spend the time to put all those plugins in. But for clinical users, I still believe that you require product sequences and reconstruction. It must be really extremely easy. And so I think it's good for advanced researchers, those packages, but not so much for clinical users. In product, we have the Fidel sequence now. On MR30.1, we have automatic pre-scan based on Bloch-Siegert. There are more nuclei, 32 received channels, and then we also have a few fixes for coherent RF noise. And I'm working also on clinical sequence for both Xenon and C13 to improve both that and also other nuclei then in the process of it. And then I would like to finish my presentation with some advertisement for 2 courses. One is an advanced spectroscopy and X-nuclei MR training course in Aarhus in June. And the other one is a hyperpolarized training course. So those courses are more geared towards PhD students. It's not really a workshop, it's really a educational event. So it's a lot of hands-on and so on. And with that, I thank you for your attention. And if there are any questions, I'm happy to answer them.
Thank you, Rolf, for the wonderful presentation. Really was a pleasure listening to all the different nuclei and what is possible with them.
Thank
So
you.
if the audience has questions, you can either unmute yourself or write them in the chat. I'm happy to read them out. I'm just curious, Rolf, what nucleus intrigues you the most out of all the ones that you presented?
I mean, I mean, it's good if you can switch, because if you do sequences for C13 for 20 years, you get quite bored.
Yes, yes.
I mean, deuterium, I'm quite intrigued. I mean, sequence-wise, it's very easy, but I think the clinical application could be very interesting.
Yes.
So, yeah, if we really get a good clinical question running, being able to answer that on a 3D scanner, I think that could be quite significant. So, I mean, all the X-nuclei, they're not really clinical. I mean, we have Xenon is partially clinical. I mean, there's some reimbursement already, so Xenon is quite far ahead. Sodium, C13, and so on is not yet clinical.
Yes, okay.
I believe there's a right hand from Fishbank.
Thank you. A very nice survey of heteronuclear imaging. So you make a point about the size of the voxels being very large compared to protons, and that's a very difficult limitation to get around. So I'm curious about the ability to get different kinds of information without higher spatial resolution. For example, is there a way to distinguish white matter from gray matter by means of weighting in a way that you have in proton imaging?
Yeah, that's a good question. I mean, it depends on the nuclear. So, like sodium, we have typically real resolutions of like 3 millimeters in that order. And so for sodium, I think you can distinguish white and gray matter. Other nuclei, I mean, phosphorus is like 3 centimeter typically, the real resolution. People often report nominal resolutions. They sound much more impressive, but they're nominal resolutions. The real resolutions are usually quite low. 3 centimeter, there's no way you can separate it. I mean, deuterium is like 2 centimeters. It's very difficult to separate. I mean, you can put it into reconstruction. You can constrain it to reconstruct gray and white matter. However, if you have structured noise, I think you can also reconstruct really nicely. If you have so much information you put in, I'm a bit skeptical. If the resolution gets below a centimeter, C13, I think we can probably still separate it somewhat.
So is there a way, though, by adjusting T1 weighting, T2 weighting, et cetera, to make some distinction between different components within each voxel?
Depending on the molecules, yes. I mean, if the T1 times are markedly different, you can use that also for encoding. People do that. If the T1 times are too similar, there's no way to do it. So
Yeah,
like, I
and
mean, for sodium, people use like inversion recovery or to separate out different extracellular, but it's mostly CSF.
yeah, that actually brings me to my second question. Then I'll let somebody else ask. So in sodium imaging, you can do multiple quantum filtering, and that is another method that is used to distinguish between intra and extracellular sodium. Is that used at all in, do you feel it has any clinical application?
I mean, there was this workshop in Dubrovnik in Kaftat, and what is it? Charles Springer, he basically trashed the field. I mean, he said it's not possible to separate it. And the reason he gave was the properties, the nuclear properties, the timings are not there. And then he also, I mean, that is one of the limitations. And the other limitations he quoted was that it requires, it has the assumption that the cells are densely packed and outside it's empty. But outside the cell, there's also a lot of stuff. So he says it's not possible to separate it. There's also a paper from him, and that basically more or less killed the field. So, I mean, yeah.
I see. Thank you very much.
You're welcome.
So we have another question in the chat. Jia Zhu asks one quick question. Why do you develop dedicated FID CSI2 and FID spiral? Can I do something that FID all two can't do? I haven't used them myself, but okay, cannot read. But I see that they probably also use the FID alls recon on the scanner.
I mean, it's intended to be clinical sequences, so lockdown. So the spiral generation is on the scanner. It uses product recon for spirals, and the FitCSI2 for the ventilation is also product recon. For CSI, we are working on it to have it also as product recon. So, I mean, it's a different target group. I mean, if you want to have clinical customers using it, it must be really locked down and you shouldn't have any flexibility.
I see. Thank you, Rolf. So no flexibility. So, but I suppose I still can use FitAll2 to do those things, right?
Yeah,
Sorry.
yeah.
Yeah. Okay,
Yeah,
good.
yeah, you can do everything with FitAll2.
Great. Thank you so much for the clarification. Yeah, I saw them in your FitAll code. You specify the METI path, but I don't know why there are two different sequences. But yeah, thank you for your explanation. Great talk. Yeah, thank you.
Thank you.
Are there any other questions? So if that's not the case, I would like to thank Rolf again for this very nice presentation. And I wish everybody a wonderful evening or morning, depending from where you're joining. And hopefully see you soon at the next Kiel Imaging seminar.
Thank you very much. Have a good day.
Thank you.